All right, thank you so much. Hi, everybody. My name is Hagai Lupesco. I'm an engineering manager with Facebook AI based out of sunny California. Sometimes it's also snowy. Today it's actually snowing where I am. And today I'm going to talk to you about recommendation systems using deep learning with some examples, some code that uses PyTorch to implement neural network for recommendations. I hope you'll enjoy. I hope you'll learn some new things. And let's, why don't we get started? All right. So our agenda for today, quickly going through that, we'll start with the business problem we're solving with recommendation systems, because it always needs to start with a business problem. We'll then go into an overview of a typical architecture of a recommendation systems in the industry. And from there, we'll actually drill into exploring using deep learning for a recommendation model, more specifically a model for ranking. And then lastly, we'll look into different ways we can optimize that model. And we'll actually look into some code examples in notebooks, so we can go through a lot of details that way. The code I'm going to show you is going to be shared later, including this deck. So I'm hoping you'll be able to take some time to look into the code later and share some feedback with me or questions. Let's get started. All right, so starting with the business problem we're solving, really with recommendations, recommendation systems try to answer a basic question: what item will the user be interested in? Now, the type of item actually differs by the business, the service that we're talking about, but digital businesses really need that kind of functionality, and it can be about what product the user may want to buy on, your favorite e-commerce site, what restaurant will a user will want to go to for dinner or for a lunch, what song will you want to listen to on your favorite audio streaming service. Similarly, what movie you want to watch on your favorite, movie streaming service, or what post you will want to read, or what news article you will want to read on your favorite social media service or news service, etc. And really, the list goes on, right? When you look at the modern digital services that have, hundreds of thousands, millions, or sometimes even billions of items in their catalog, that problem becomes very critical, and that's where machine learning plays a key role in making sure that content, that huge amount of content, is personalized. Now, further discussing the business problem, the business value businesses, services, systems achieved through recommendation, there are really three main key business metrics. The first one is engagement. How much is the service able to engage customers for a good amount of time, giving them good value? YouTube estimates that 70% of the time watched on YouTube is driven by the recommender systems, which is a very large number. When you look at retention, or a service's ability to retain customers on their platform and avoid churn, Netflix, as an example, estimates that the recommendation systems and algorithms save more than $1 billion per year in subscriber churn. And lastly, revenue. 35% of the purchases on Amazon are estimated to be the result of the recommender system. So clearly, recommendation system are able to move the needle on metrics such as revenue as well. So these are three high-level business metrics that recommendation systems typically try to move and improve. Okay, now that we've established the business value and the business need, let's talk about the technical details of how these recommendation systems are typically set up. There's really two main systems at a high level that are involved here. The first one is the offline system, the machine learning pipeline that is used to build the models, train it, evaluate it. The objective of the offline system is, first of all, to produce an up-to-date and accurate model. Secondly, to evaluate that model to ensure that the results of the models are good enough or better than the previous model, etc. And lastly, to take this model and publish it so it can be used in production for online serving to actually engage with real users. If you look at the diagram here, you can see a simple diagram of how this offline system is typically set up. We start by data reading, the training data, and validating that data, so to ensure it's not corrupted and there's no other issues with the data. That data is then passed to a system that does feature analysis, feature transformations to make sure that data is ready to be fed into the machine learning or deep learning model for training. Next comes the training of the model, the tuning of the training. The output of that stage is a trained model. That model is then evaluated to look into the offline metric to ensure the results are as expected. And if it all looks good, then from there, the pipeline would publish this model to the online system where it can actually serve actual traffic. Now, the thing about this is then it starts all over again because the reality, especially in recommendation systems, is that the landscape is always changing. There's always new items that are offered on the platform. There's also new users. Users are changing with their preferences, their interests. Items are changing with their, in a lot of respects. So all of this needs to operate continuously. The frequency of this, cycle depends on the specific business and the specific domain. But in most production systems in the industry, these things are recurring. The metrics for such a system, first of all, it's the offline model evaluation or model accuracy, and there's different metrics. Again, it depends on the business use case. It can be, root mean square errors or precision or recall at k, etc. There's a bunch of other metrics. And then there's system reliability, which looks at things like what's the failure rate in this pipeline? What's the mean time between failures? And there's a bunch of other metrics. That's also important, especially for systems that need to, churn out lots of models, per day, which is like the scale of the larger player in the industry. That's what is needed. Okay. The next system that is part of that recommender system setup is the online system that is typically used for serving and for logging. The objective of this system is to, of course, improve the actual business metrics through the recommendation system recommendation models. Previously in the offline system, the evaluation is for offline metrics. It doesn't necessarily mean there is any change for the real business metrics, and that's what the online system tries to achieve. Another objective is to pick tens of items, typically out of a much, much larger catalog. That catalog may be in the millions or more in terms of number of items. And the system needs to do that within pretty low latency, especially for online. We want to minimize the time from when the user opened their app or navigated to a new view in the UI until the actually items are rendered and presented to the user. So this system has a pretty tight latency budget. And then lastly, another last objective of the system is to log the user interaction, the content the user was presented to. And we want to log that for both online evaluation, but also so we can use that data later for the offline stage for offline training. In the diagram here below, you can see a very simple diagram. A request comes in from the device. It goes into the recommender system. First, there's retrieval, which is trying to retrieve typically dozens, of items out of a very, very large catalog. That output goes into a ranking stage that does more higher accuracy ranking of each of the items. And then that result is going through a set of business rules. Most actual businesses have a set of hand-curated business rules to maybe filter things that the user has explicitly said they're not interested in seeing, or filtering out things that maybe do not meet the services different criteria, say, for this specific segment of customers, or maybe even to promote or demote certain content based on certain business rules. And then that output is put into a ranked list of items and set as a response back to the device for rendering. And of course, it's also logged so that we know that, hey, the user was presented with this set of items. Interactions the user had are also logged in that system. The metric for the online system is first and foremost the business metrics like engagement, retention, revenue, click-through rate, etc. System performance is another key metric. What was the end-to-end latency? What was the memory usage, CPU utilization, etc. And of course, as always, reliability, which is always a key metric in such systems. Now, in this talk, we're actually going to focus on the ranking stage. So in the previous slide for the online serving system, we looked into the multiple stages. We're going to zoom into the ranking stage, but we're more specifically, we're going to talk about how the model that typically handles ranking, how is it authored, how is it evaluated, what are ways to improve this model, and it's all going to be focused on using neural networks to implement that. Okay. So let's dive into exploring how a deep learning model can be used for ranking. We'll start with an example use case of movie recommendation. The business problem here is recommending a handful of movies to watch out of a much larger catalog in order to drive engagement with the service, retention, customer satisfaction, etc. If you look at more technical definition of what we want to solve here, is really given a user in a movie, we want to be able to predict the rating this user would rate this specific movie had the user watched that movie, right? So that's the task we want to solve, and of course, solving this task will allow us to pick a set of movies that we think the user will actually enjoy viewing. There are different alternatives. We could have defined this problem a bit differently, like predicting probability of just user watching the video, sort of a binary classification problem, or predicting whether the user will, like the video or will share it. And those things are done in the industry, but to keep things simple, we'll focus on the task of star rating prediction. We got to use some data to build our model, and we will use MovieLens data set. MovieLens, if you're not familiar with it, it's a data set created and maintained by the GroupLens research group out of University of Minnesota. And the deck, which I'll share later, has a link to this. I can quickly open this here. They have a nice couple of web pages that gives you a lot of explanations. There's actually multiple flavors of this data set. And they also have other data sets for recommendations. So I highly encourage you to check this out. Okay, so let's zoom in on the MovieLens data set here. So as I said, MovieLens actually has multiple versions of their data set. We will use, in this example here, the one targeting education. So it's ml-latest.zip. It's not too large. It's around 260 megabytes in size. It contains 27 million ratings of actual users who actually rated movies, covers 280,000 users, and a total of 58,000 movies. So it's not extremely large, but it's also not too shabby. One interesting thing to note is that the sparsity of this data is extremely high, right? If you look at all the potential pairs of users and rating movies, it's actually much, much larger than 27 million. The sparsity, so the percentage of potential ratings, user movies pair that have ratings, is actually extremely low. And we say that this is a high sparsity problem. That's a typical challenge with recommendation system. Usually you have extremely sparse data. It's one of the interesting challenges here. We'll look into this with a bit more details. Let's open up a notebook where we can actually take a closer look at the data. The links to these notebooks, I'm running them in Colab, but later on I'll share the deck and you can go through the code yourself and run it. So in this notebook, we basically do a very simple data analysis to just get to know the data a bit better. We start by this cell, just loading the data, right? So I'll quickly skim through this. I've executed these cells before. We can just look at the results. So this step loaded 27.7 million ratings and 58,000 movies. We load the data into data frames, pandas data frames. And if you look at the ratings data frame, we can see that it maps user ID and movie ID into the rating with a timestamp of when the rating was given by this user. And you can see users have may rate multiple movies, etc. The maximum rating has been 5, the minimum rating 0.5, and there's 53, close to 54,000 movies that have at least one rating, meaning some movies don't even have ratings. We have a movies data frame. We can see the movie ID, the movie title, which is omitted here because there's not enough space, and also a set of tags for the genres. Here we calculated dataset sparsity. It's extremely high. There's potentially 15 billion ratings, but we have only 27 million. So that's where the high sparsity comes from. Here we can see a visualization of a small set of the user item matrix, right? This is, of course, a part that is a bit dense, right? Every column here is a movie, every row is a user, but as you can imagine, most of this table actually has nones, right? Because it's extremely sparse. You can see that there are a few movies that have extremely high number of ratings, right? Like Shawshank Redemption, Forrest Gump, Pulp Fiction. And then there's also a lot of movies that have very small number of ratings. Some even have 0, which is not surprising, I guess, because of the popularity bias. And if we look at the histogram of the number of ratings, we can see that the majority of movies have just a few ratings, right? We can see this here. If we take a closer look with the log scale, we can see that long tail, how it unfolds. That's one attribute of this specific data set, I guess, is that majority of movies have just few ratings. And if you look at the rating histogram, we can see that it kind of resembles a normal distribution. Average rating seems to be around 3.5. And this is another interesting plot showing the relationship between the rating and the rating count. We can see that probably movies with higher ratings tend to be rated more often, and that extreme ratings, both high and low, tend to have just few ratings. So those are interesting attributes of the data. It's always important to kind of get a better understanding of the data before you actually start the modeling. Let's the next step, it's always good to start with some kind of a baseline. In this case, we'll start with a baseline, very simple baseline, popularity-based baseline. And this baseline would work very simply. That model, given a movie, will predict the user's rating for that movie to just be the average rating across all other users who rated the movie. And as you can see, obviously, there's nothing personalized in this model, right? It doesn't factor in any special preference or attribute the specific user have. It's just based on what everyone else thought about this movie, everyone else who watched this movie. It's not a very good model, but it's a very simple one, and we can use it as a baseline. So there is a notebook that actually linked here that actually implements this popularity-based model. It's very simple, so we'll save some time and not go into it. One thing to note is that to evaluate this model, we split the data into 80% is so-called the training set that we use to compute the average rating. The testing, we use 20%. And we evaluate model accuracy using a root mean squared error metric, evaluation metric. And this model accuracy with this method is 0.965. All right, there's a notebook that shows you all these details. So pretty quickly and easily, we're able to get to a baseline model. It's not too good, but it may not also be that bad. The key question is, can we use machine learning? Can we use deep learning to do better? All right, so with that question in mind, let's look into neural collaborative filtering, NCF. NCF was introduced in a 2017 paper, which is linked here, and the diagram on the right is actually, I took this out of the paper. And it shows the architecture of this NCF model. The highlight really is there are two inputs that takes user ID and item ID. In this case, in our specific case, it will be a movie ID, and it maps the user and movie IDs into embedding through embedding layers that project these sparse inputs. These IDs are really sparse inputs. Projects them into dense vectors. Through training, we want to ensure that these dense vectors actually learn latent representations of these inputs, so of the user and of the movie. Then we concat, this architecture concats these two dense vectors together and feeds it into a multi-layer perceptron in order to capture the user-item interactions and learn these interactions. The output layer is just a single neuron that outputs the score, which is the star rating. The user would rate this movie. And of course, we train this with our training data. So this is the architecture proposed by NCF. As a side note, I would say that NCF paper actually proposes an additional, more advanced design, a NeoMF, which you can actually get better results using it. In this session, because of lack of time, we won't dive into this more advanced architecture. It can be an exercise you can do later on. It's pretty simple to do it with the baseline that we go through here. So now let's actually look into how we can use PyTorch to implement this architecture and to train this model. So let's open this notebook. To run this in a reasonable amount of time, you'll need to run this with a GPU, especially as the architecture becomes more complicated, more complex. But these cells have been run before. Let's just go through it to go through the code. So we start by data preparations, which is very similar to what we've seen earlier. We're loading the movie lens data set. There's a function here that handles that. We load the same data set with 27.7 million ratings, training samples. Clicking into the data like we did before. I'll just scroll through this. Now let's start actually by creating our data set and making it ready for training and for a test. So we're creating the input and label data. So X is the user ID and movie ID, and Y is the rating for that pair. Okay. Just want to make sure. All right, we can go to the Q&A later. Let's continue here. And then we use scikit-learn utility function to split this data. So 20% goes to test and the rest 80% goes to the training. So this here shows that creation of that split, and we have the data sets ready for training. Next step, let's do the model authoring, where we actually author the neural network, author our model, and we'll implement NCF as we discussed before using PyTorch. So I'll quickly go through the code. First thing, we define a class that extends PyTorch's nn.module. We'll call this class Neural Collaborative Filtering Net. And in our constructor, we take two mandatory arguments. One is the user count, the number of unique users in the data set, and the other one is the movie count, number of unique movies. Then there's a set of optional arguments that really allow us to control and tweak and tune the architecture. So these are the architectural hyperparameters for the size of the embeddings, for the number of hidden layers we have in the MLP, for the dropout rate we'll use for regularization, and for normalizing the output. So we can take it from a 0 to 1 range, which is the output of the net, into the 1 to 5 star rating output. If you look at the implementation of this constructor, the init function, first we create the user and movie embeddings in PyTorch's nn.embedding. The two arguments, one is the count of the users, the other one is the embedding size, which is one of the architectural hyperparameters. Similarly, we do the same for the movie embedding. We then have an internal utility function we built for generating the MLP. which basically takes the embedding size, the hidden layers, the dropout rate, and constructs the MLP out of that. We'll get to see that in a minute. And then if either we want to create a dropout, if there's a dropout rate specified, we also add a PyTorch and then dropout. We'll look in later in this talk. We'll look into dropout in a bit more details. This section handles the normalization of the output of the neural network, and then lastly, we have an internal helper function to init the parameters of our neural network. This helper function generates the MLP. It takes the embedding size, hidden layer unit, dropout rate, and basically just with a simple loop iterates through the number of layers, and then just creates PyTorch nn.linear for the linear, and then on top of that, the nonlinear activation function, which we use ReLU. The paper looked into different nonlinear activations and determines that ReLU works best in this case, but you can also play around with other types of nonlinear activations. And if there is dropout, we also add PyTorch's nn.dropout with a specified dropout rate. All of these are combined together into the MLP and then bundled into a PyTorch nn.sequential, which is then returned and is constructed as part of the model. This function initializes the parameters, nothing unique here. We use Zapier uniform to initialize the MLP, and then we use uniform sampling to initialize the embedding tables. You can actually choose more sophisticated techniques that may help a little bit, but we won't dive into this here. And lastly, the forward function that we implement for the forward pass. So that forward pass takes the two inputs of our neural network. One is the user ID, the other one is the movie ID. And pretty simply, first of all, it takes the user ID through the embedding table and then returns the dense embedding vector that represent the user features. We do the same for the movie ID to the movie embedding, and then we get these two vectors, the user features and the movie features. We then concatenate the two to create a longer vector that we then feed into our MLP, the multi-layer perceptron. And the output of that is the output of the MLP, which is a scalar value between 0 and 1, which we take to our normalized output function that basically shifts and scales that to be in the range that we want for star rating, so 1 to 5. And then that value is returned. That's it. That's the definition of our neural collaborative filtering model. You can see that the way to instantiate this is very simple. You just call the constructor, we give it the user count and the movie count. Here we actually print the model, so we can see here the architecture that we've created, two embeddings, one for user, one for movie, then MLP. In this case, we use the default value, so there's no dropout, so we do not see the dropout rates here. But if we would have provided dropouts or different architecture, of course, it would be evident. The number of model parameters in this case is close to 11 million parameters, and the model training size is around 40 megabytes. So it's a fairly small model with pretty low computational complexity. Most of the size of the model actually is within the embedding tables. Yeah, this section, this cell just does a simple dry run prediction to make sure that our model is working as expected. Of course, we haven't trained the model yet. So in this example, we can see that for user ID for the 47642, movie ID 648, the prediction of star rating is 3.4 more or less. The actual rating was 3, but of course, this model is not trained. We just wanted to do one dry run to make sure it's, we can do a full forward pass and it's working. The next step is actually for us to train the model and to evaluate it. So this cell here creates a data set batch iterator that iterates over our data set in batches for training. Pretty simple. I'll move forward here. And in this section here, we actually start by initializing the parameters of the model. by setting the mode into train mode. It's important to call this so that PyTorch knows to activate the modules we're using and the functions we're using that are only used in training. One key example is dropout. We want dropout to work only on training, not in evaluation. We continue by setting hyperparameters like learning rate, weight decay, batch size, number of epochs, etc. We set some training loop control parameters that we'll use later on. And then I'll just scroll here to another important thing, defining our loss function and optimizer. So the loss we'll use here is MSE, mean squared error. And the optimizer we'll use is Adam with the learning rate and weight decay we discussed earlier. Again, you can change these based on the business use case. You can use potentially a more sophisticated optimizer. But we're going with the basics here. And then we have the training loop, which iterates through all of the data in each epoch. Every epoch, we do a pass on all the training data, update the model parameters, do a forward pass, backward pass, update the parameters, continue. Once we complete that, we do a test pass where we actually don't update the model. We just capture the loss on the test data and capture that metric. And at the end of that, we actually look at the learning curve. So as you can see here, this training was run before, and you can see that the train loss started by 0.75, the validation loss by 0.7078, and then every epoch there was a slight improvement. If you look at the visualization of the learning curve, the blue line here represents the train loss across the epochs, and the orange line shows the test loss across the epochs. And we can see that the minimum test loss was achieved in actually epoch 3, which is pretty early, and we'll talk about that in a minute. But that's where we stopped our, after we saw that there is no improvement after 3 epochs, we stopped the training. We implemented early stopping here. And then we move on to compute the model accuracy using root mean squared errors, which is our model accuracy evaluation metric. And the root mean squared error here is 0.8208, which is actually better than our popularity model baseline that we discussed earlier. Okay, let's go back to our slide. So, we looked into the code, how this is implemented with PyTorch. We actually trained the model. Just to summarize, we used 27 million samples, 80% of them used for training, the rest for validation. We had a pretty simple architecture, 32 embedding size per feature, 4 dense layers, relay activation. We used Adam as our optimizer, MSE as the loss function, and there's a bunch of hyperparameters we use for learning rate and weight decay. The results show that root mean squared errors of 0.821, that's actually 15% better than our popularity model, which is not bad for such a, kind of a simple model we started with. If you look at the learning curves here, you can see that we can do probably much better, because we can see that there's potentially, very fast overfitting here. So the question is, can we do better? There are things we can do to actually optimize this model further, and we can think about that along 3 main dimensions. One of them is the data dimension. We can use more data, we can use better data, we can take in additional features so we can learn more from these features. And there's other things we can do with the data. The model itself, we can help avoid overfitting using regularization. We can increase the capacity of the model so it's more complex and potentially learn better relationship between the user and the items. We can use more advanced architectures and other similar things we can do. And lastly, on the algorithmic side, we can tune the hyperparameters to optimize them more. We can use a different type of an optimizer. We can use more sophisticated initialization, and there's other things we can do on the algorithmic side as well. Let's take a look at a few of these things quickly. So if you use more data, as we discussed earlier, we can see that our NCF model, the one we started with, may be overfitting, but we can see it achieved minimal loss after just 3 epochs. We can see that the train loss after that continued to improve while the evaluation loss got worse. It's a very clear signal that our model is learning the noise and is overfitting. And in this case, additional data for training is likely to help our model avoid overfitting. So if you look at results here of running the same model with increasing number of examples for training, shows that it pretty consistently helps improve the model accuracy. If we increase our examples by 14%, our root mean squared error improved to 0.816, which is 0.6% better than the NCF baseline we started with, much better than the popularity model, of course. So in this case, we can see that more data is definitely helpful. Maybe best data is just more data. And that's one key thing. Let's look at another aspect that we discussed, increasing the model capacity. So with more model capacity, we can enable the model to learn more complex representations of users and movies. We can better learn complex relationship between the features, between users and movies, and if we have other features also between these features. And there are different ways we can increase the model capacity. We can increase the embedding size in our embedding tables. We can increase the number of layers, the number of units in each layer. We can introduce new interactions between features. The downside, and where we need to be careful, is that this can help the model overfit much more easily even than what it the overfitting we already saw. It can also increase the training time and hardware cost. And it can also increase the inference latency. Those are all considerations to think about. If we look at some results, this diagram here shows a few experiments with increasing model complexity, model capacity. So from the left, it's the simplest model, and then as you go to the right, you can see that the complexity of the model increases. And the red dot shows the model accuracy, the root mean square errors of this model as it grew. Now we can see that there has been improvement in the model accuracy, although it seems like the improvement is sort of diminishing. But overall, when we increase the model capacity by 4x, our root mean square error improved to 0.816, which is 0.6% better than the NCF baseline. So to summarize this part, bigger models can be better sometimes, right? And the thing to watch out for here is overfitting, which, as we saw, you can avoid by more data and also by other techniques, which takes us to the next step of improvements using regularization. So our model was overfitting, and one way to overcome that is to introduce regularization. And there are multiple ways you can introduce regularization. One of them is dropout. It's a technique introduced by Srivastava and Hinton in 2014. The diagram here is taken from their paper, and with dropout, we randomly disable some neurons in the network to kind of make the neural net more resilient and less, there's less likelihood it will overfit. Using dropout in PyTorch is pretty simple. PyTorch provides nn.dropout. We just add that layer in the model init, and when we looked at the code earlier of our model on PyTorch, we actually seen the code to add dropout. We invoke it in the forward pass. And then one important thing to remember is don't forget to call ncf.eval or your model instance.eval when you're doing evaluation, because it's important to disable dropout when you're doing evaluation or when you're doing inference. You want dropout to be active only when you're doing training. So if we look at the results here on the right, the upper graph shows the original training curves without regularization. So you can see that there's pretty early on there is overfitting. The graph on the lower graph shows the same network with dropout regularization. I think it was using probability of 0.25. And you can see that mostly our overfitting went away. You can see the test curve actually continuously improves, and it runs for more than 40 epochs, which is a really good sign. This is a much healthier learning curve compared to the one above. If you look at the left, the results when applied regularization to a more complex NCF model actually improved quite significantly our model accuracy. Okay, putting all these improvements together, so increasing the number of examples, increasing the model complexity, adding dropout regularization, actually yielded pretty nice results. You can see that the root mean squared errors of the overall improved model is 0.804. There was 2.1% improvement versus our baseline NCF and 16.7% improvement versus the basic popularity model. And if you look at this learning curve, it's actually much, much healthier than what we've seen earlier. These improvements does come with a cost. The model size grew 4x, training time grew 24x, right? And with it also the training cost. So this is one thing to pay attention to. These improvements does come at a cost. We can do more things to optimize, like improving the data, using additional feature, using a better architecture, like even the one called out in the NCF paper, and doing hyperparameter tuning, and lots of other things. In this talk, we looked at more the basic things, and of course you can take this further. Now, how does this compare to the reality, right? Doing a reality check compared to the industry. So the reality is that the key industry use cases at large-scale online services actually requires around 1000x the scale of what we've done here. Examples are not in the millions, but they can be in the trillions. The number of users can be in the billions. The number of items in the millions, or sometimes some catalogs also have items in the billions. And also there's many, many more features to learn from. Here we learn basically two basic features, the user ID and the movie ID. But in the real case, you'll have many more features to learn from. And in the industry, we scale to these requirement through multiple things. We use high capacity hardware. We use scalable software infrastructure. We use advanced distributed training, things like model parallelism and other optimizations of the training loop. And we use efficient serving by compressing the model for serving, using different optimization, using hardware acceleration for serving. With all that said, the principles are pretty much the same of what we went through in this talk. We're at the end of our talk. I hope you enjoyed. I hope you learned something new, and that you'll be interested in exploring this more. I wanted to thank you for the time. And one last thing I will say is that I'm available on LinkedIn. I'd love to hear from you, get feedback on this talk, hear from you. And lastly, Facebook is hiring for machine learning roles. There is a lot of exciting AI work done in Facebook on both the system side and the modeling side. And I'd love to hear from you. If you're interested in exploring opportunities, please do reach out. You can find me through LinkedIn. I'd love to hear from you and help you find a good spot for you in Facebook AI. Thank you very much.